Hello everybody, I'm back. Today we're going to be looking at a problem that deals with changes of energy, changes in temperature, heat, the first law, that sort of thing. Kind of a big old practice equation regarding these particular parameters. So our setup for this particular problem is that we have a box that's placed in an ice bath. We have a small membrane separating the two sides of our container. On the left side, we have 5 atmospheres worth of helium, and on the left side, we have 1 atmosphere worth of argon. That particular container inside of the water bath is 80 centimeters in length, and the membrane, which can be shifted left to right by a piston, starts at a position of 30 centimeters from the far left side of the board, right? Or far left side of the container. So both sides occupy some amount of space. We are asked to find a couple of parameters from this particular setup, namely what the change in temperature of the water is, what the final position of our piston will be if we allow pressure to act and let that piston move inside of our container. And then lastly, what our final change of entropy of our system will be, right? So let's tackle the first one, right? So for the first one, we know, as a matter of fact, we can just go straight from the first law, that our change in energy is equal to our change in temperature minus the work done onto the system, right? We know that there isn't any work done onto the system because the containers themselves are not changing any sort of volume. Like, yeah, you can make the argument, yeah, the helium is going to increase in volume, argon is going to increase in volume. The water, though, isn't going to increase in any sort of volume. That's just not happening. So there's no work being done onto the water itself, right? So that just leaves us with Q. And then we know, just in general, that our change in heat, delta Q, is related to the sum of the masses present in our system times their molar specific heat times delta T, right? So the thing about this, though, is that we're trying to think about what the overall change in temperature is going to be. And we have a thermally isolated system. So if we are doing something inside of our thermally isolated system, move stuff around, right? There's going to be some change in entropy, obviously, within that system. But it's going to want to return back to some sort of equilibrium afterward, right? It has to. So because we know it needs to return back to some sort of equilibrium after we allow that piston to move, we axiomatically know, just from principle, and we can reason this, we don't have to mathematically show, we can just reason the fact that the change in temperature has to be equal to 0, or rather that the overall change in the energy of the system itself is equal to 0, which is what we can do to mathematically show it if we want to, right? So we can deduce that there's not going to be a change in temperature, but if we show it, we just set delta E equal to 0 because there's no overall change in energy in the system itself, but we can write out our sum of our heats. I did this for brevity's sake and for the sake of keeping my board nice and compact. But we can just write all these guys as the sum of the masses and the sum of the molar specific heat. And then I just pulled the delta T out. So we know that our masses and our specific heats are non-zero numbers. So the only reasonable mathematical solution to this is that the change in temperature delta T is equal to 0, right? So the temperature of the water isn't going to change even if we allow the piston to move inside of our box. That's all we're showing with this particular question. The second question is a little bit more mathematically involved than the first one. This one, you kind of have to set up a few particular states. You have to look at the initial state of the system and then the final state of the system, right? So we're asked to find the final position of the piston. So as we allow pressure to be exerted on the piston from the left-hand side, it's going to want to push and push and push that piston further down until there's an equal amount of pressure on both sides, right? And that will be at the equilibrium position, which I just called L sub E. And obviously we can get this quantity and how we define it. We can say that volume is our standard, length times width times height value, right? and then we can compress two of these terms into a surface area of our piston. We don't really care about the surface area of our piston. It's just some fixed number that we're just going to call A, right? We are interested in L. So at equilibrium, we can say that the pressure of some of either one of these sides is equal to the equilibrium length times the surface area is equal to the number of moles, RT, from our ideal gas equation, right? Now, what we're interested in is trying to figure out a way to find this particular equilibrium condition. And one way to do that is by taking ratios of terms. That's a really good problem-solving strategy. If you have two terms and you need to get them in terms of one another, sometimes it's useful just to divide one by the other, and then you can pull out the terms you need so you can reparameterize them. And that's the strategy that we use in order to solve this problem. So we take our equilibrium position of our helium, right? We'll give helium its equilibrium position, and we'll say that that the remaining position at equilibrium will be the entire length of the container minus how much the equilibrium position has moved, I guess, for lack of better words, or where the equilibrium position winds up at. That's a better way of saying it, right? So if this is equal to dividing one another, the pressure times the volume, then the right-hand side has to be divided by one another, right? If we're in equilibrium, like we've discussed, the change in temperature is 0, so they're going to have the same final temperature, so we can just nix the ideal gas constant and the constant temperature, and that just leaves us with a molar ratio of the number of moles of helium to the number of moles of argon. We don't know yet this particular numerical value, but we can actually get it using the initial conditions that we have of our system, right? So we know that we have an initial pressure of helium being 5 atmospheres. We know it has an initial position of 30 centimeters. We also know that our argon has a pressure of 1 atmosphere initially, and it has an initial position L sub ARI. I know it's awful notation, I know, of 50 centimeters, because 80 minus 30 is 50. So what we do is we just plug that in, and I've kept things in terms of meters here and atmospheres, and that gives us 3. So that's how we know that the ratio of the number of moles of helium to the number of moles of argon is 3. I might have said earlier that we had 1 mole of helium. We didn't know that yet. We do know this ratio now. So now that we know that this particular ratio holds, we set 3 equal to our condition here, right, at equilibrium, where we have the pressure of helium at equilibrium times the equilibrium position L times A, same for argon, and then 80 minus some equilibrium position times A as well. Now it's pretty clear to see that from this condition our area terms should cancel out because we have the same surface area on either side of the piston, right? And then at equilibrium as well, because if we're at equilibrium, there's going to be an equal amount of force being exerted on either side of that piston, so it's not moving anymore. The pressure of the argon and the pressure of the helium at that point also has to be the same. So because it's the same, then we can just, where is it? Yeah, we can just cancel these guys here too, right? So now what we have is this ratio of 3 is equal to the equilibrium position divided by 80 minus the equilibrium position. And then after doing some algebra, we move this guy up here, we FOIL it, get like terms together, and we solve for L sub E, we'll find that the equilibrium position, and I need to write that down, equilibrium position is equal to 0.6 meters, or about 60 centimeters. So what that means is that the piston will have moved from a position of 30 centimeters from the left to 60 centimeters to the left, right? So, part C asks us to find the overall change in entropy for this particular system. And in order to find the overall change in entropy for this system, we need to look at some of our definitions for entropy. And there's 2 in particular that are really handy, and I derived them in my homework. I didn't derive them here because I didn't have it in the board, enough space on the board. But nonetheless, we can say that our change in entropy is equal to the number of objects in our system times K, being the Boltzmann constant, times the natural logarithm of the number of accessible states, which we can also usually just write as VF or VI. I just wrote omega there because I was thinking kind of quickly. But we also know that N times K is equal to the number of moles of system, moles in the system that we have, times the ideal gas constant R. And we know what R is, but we don't know what number, we don't know N in particular, because we don't know the number of molecules off the top of our bat. So it's more convenient to just use the ratio of the moles that we already have accessible to us instead of trying to actually calculate the raw number of particles. So using that definition, we know that the total entropy change is the change in entropy of the argon plus the change in entropy of the helium. And when we plug those numbers in, we can get this final algebraic expression, right? So assuming we just have this ratio being true, then we just do some, algebra to find that there are 3 times as many, or how do we want to write that? Well, we just say that 3 times the number of argon's moles is equal to the number of helium moles, and then we can move things around. We find that there's about only 1/3 the number of moles of argon as our number of moles of helium, right? So that allows us just to plug in 1 for helium and then 1/3 for argon. And you can throw that into a calculator, and if it should give you a number that is bigger than 0, hopefully. And if it doesn't, then I've done something demonstrably incorrect. But regardless, that's what you should get for your final expression. Right, so you can just sum the total entropies together. So yeah, with that in mind, we can use the first law to get expressions for change in temperature of some thermally isolated system. We can play around with the units in the ideal gas law in order to find mechanical quantities like length or change in length, right? Or in this particular case, an equilibrium position. And then lastly, we can just use a simple expression for total entropy in order to find what the overall change of entropy for a system is. Thank you.